Warm greetings to the International Mathematics Masters in Lahore. So my name is Gabriele Benedetti, and I will be the instructor together with Alberto Ambondandolo for this second part of the class Introduction to Complex Analysis. So unfortunately, we cannot come to Lahore. It's a shame, but I hope that we will meet in the near future when this situation is resolved. So we will have during this 2 weeks online lectures and exercises. But before all that, I would like to maybe present myself in a couple of sentences and using some video support. So I come from the University of Heidelberg in Germany, and I am here now since 2018. I'm a junior professor, and if you can see this on the map, Germany is where the little heart is. So it's a small city, 130,000 inhabitants, but originally I come from Rome, which is here below. And I've been there for the first 20 years of my life, and then I moved to Pisa here to study. And after that, I did my PhD in Cambridge, in the UK, close to London. And since 2014, I moved to Germany, where now I've been for the last 6 years. I've been to several cities as a postdoc, and now I am in Heidelberg. If you want to contact me, so my mail it's written here for questions or any type of comments. I will be happy to answer. And let me continue with my introduction by telling you what are my mathematical interests in my research. So I like to study geometry of spaces using methods from analysis, and this is referred to as differential geometry. And you have seen some instances of this type of study already in this class. So you have considered length of curves, and this is expressed as the integral of a derivative. So you see here that you can use analysis to define some geometric quantity like length. But you also have seen, for example, how the complex plane and the Riemann sphere are related to each other. And we will see actually in the second part of the course also some hint to another geometric construction, namely the hyperbolic plane, which you can represent using the unit disk in the complex plane. So let me now give you some short overview of what we are going to do in this second part of the course. So in the first week, we are going to deal more with the analytical part of this class, and we will study singularities of holomorphic functions. And here, the lectures will be given by Alberto, and I will take care of the exercises. So let me say maybe a few words of what is this part about. So you've studied already that when function f is defined on a disk, then you can use the Taylor expansion of this function in infinite series if the function f is holomorphic. And now we want to study what happens if the function f is holomorphic, but only at the complement of a point. So we assume that this is holomorphic on a disk minus a point. And now we don't have a Taylor expansion anymore, but we have something more general called a Laurent expansion around the singularity Z0. And this will be very important because then we will be able to define a number called the residue of f at Z0. It's a complex number. And thanks to this number, we will give a number of applications. So one application is to compute integrals as series. So there are some very important integrals in, for example, in real analysis that can be computed very easily once we can handle residues. Another important application is that the residues give us a way to locate zeros of holomorphic functions. So let's say we have a polynomial, so we want to know where its zeros lie. We can use the theory of residues, and still many more applications that, time permitting, we will also see. This is the first week. For the second week, we are going instead to look at geometric properties of holomorphic functions. And here I will be giving the lectures and Alberto the exercises. What is the rough theme of this second part? So suppose we have now two regions in C, so some region U1 and U2. And now we ask if there exists some holomorphic function f mapping one region to the other with an inverse doing the opposite job. So we want a bijective holomorphism, so something is called biholomorphism, sending U1 to U2. And here we will consider mainly concrete examples. So we can have C, we can have even consider the Riemann sphere. In this case, we will have the theory of Möbius transformations. And then we have other important examples, which are the disk or the upper half plane, so the points with imaginary part of z bigger than 0. And in order to study when such maps exist, we will use several properties of f. And one we already seen is the maximum modulus principle. Another one which will be very important is the preservation of angles, which basically means that if we have a point in U1 and two curves passing through these points, then they make an angle at the point, and we can look at the image of these curves under the map F. They will pass through another point, and the key property now is that these two angles are the same. So the angle here at the beginning and the angle here at the end. So this is what we are going to do in these 2 weeks. And now in the first exercise hours, I want to just maybe break the ice and look at the solutions of the midterm exam and try to solve them together with you. So see you next.